Hello, my name is Choate, and my group members are Melone and Ritchie, and we're going to go over this big data final project. So a little bit of the data sets overview. So we're going through four stock markets, and our first one is going to be Google. So a little bit about it. Real quick, jump to my screen. So Google, the ticker is Goog. Full name is Alphabet Inc. Class C. That's what it's now under. It has 36,000 change data points with date range between January 1st and February 28th, 2025. It's minute level data, so every minute there's new data. And the asset type is large cap tech stock with low volatility and stable high volume trading. It is a strong fundamental business. So here's a little bit about the time series data of the stock. As you can see, it has ups and downs. Unfortunately, in March 2025, it went down overall. So 10-minute stock price, this is solar stock, and it has 93,000 and some change data points from date range between November 1st, 2024 and October 31st, Halloween 2025. It's again a minute level intraday data, so it's either between a minute and 5 minutes, and the asset type is solar energy with moderate volatility. Has its heavily influenced by renewable energy policy and oil prices. And here is the time series data of this. It's been going up as of November 2025. And SOXL minute stock price, as I explained, that's a ticker, and it's a Direction daily semiconductor. It has 2,731 data points, by far the smallest data set of the group. Has its dates ranges between October 31st and December 1st, 2025. It's minute level intraday data, so again, between a minute and 5 minutes it's get recorded, with the asset type being 3 times leveraged ETF. It's extremely high volatility, has its resets daily, and it's not necessarily known for long-term holding. And here is the time series of this data, so extremely volatile, like I said, and it's not really known for long-term holding. And an XRP data set, and its full name is Ripple. It's 185,655 data points in date range between June 17th and December 7th, 2022. It's intraday data, like I said, 5 minutes and 1 minute time variables between each data point. And it's cryptocurrency, and therefore it's extremely volatile. There's no market close, there's plenty of crypto market swings, and the high volume spikes during market events. It's influenced by regulators such as the SEC and decentralized assets overall. So as you can see, you're very volatile. I mean, you can see this huge spike between September and October 2022, and the huge spike downwards between November and December. So here's our models, a little bit with the models, and part 1A is deep learning and architecture and justifications of why we did this. So a little bit of the DNN model. We chose to utilize the DNN model as it is fully connected feed-forward network between multiple dense layers. So theoretically, it can learn any function through approximation, and it can learn nonlinear relationships between activation functions. We thought it was a good testing point to see if simple nonlinear combinations of features can predict prices overall, and it works well when technical indicators such as MA and RSI capture time patterns. We felt that the DNN may perform well on stable stocks such as Google with clear patterns, but will struggle with pure time series dependency as it has no memory to consider sequences. And so here's a little bit about the parameters we chose for our DNN model. We chose layer widths of 64, 32 to 1, because we felt 64 units was sufficient enough capacity for the 4 OHLCV features. 32 units, to force feature selection with an information bottleneck of 1. We set a dropout set to 0.2 for a standard starting point. And we chose leaky ReLU over normal ReLU as prevents the dying ReLU problem. So a negative slope allows a small gradient flow for negative inputs, and stocks can be negative, necessitating the need for the gradient flow. We also felt that this was a baseline comparison, which would be a great starting point in comparison and creating the other models. And it also tests if patterns exist with time modeling. So here's our CNN models and some justification why we did this, which shows you the CNN model has a good local pattern detection, finds short-term trends and patterns such as track trends and price trends and momentum shifts. While originally designed for images, we can adapt it for sequences. And because stock prices have repeating local patterns, we feel CNN can capture and predict well potentially. It also has robustness to position. A pattern at one time step will be detected equally and can be considered more efficient than other neural networks, as it has fewer parameters than fully connected networks. So here's a little bit about the model we did ourselves. Has convolution layers from 32 to 64. That should be a 64 at the top there. 34 filters to detect local patterns such as trends, reversal, spikes, and 64 filters to combine patterns into complex features. Doubles has a standard practice in CNN architectures. Shows a kernel size of 3 to capture short-term momentum, but it's not too large to blur out important local changes. Shows max pooling, as it selects dominant features and reduces parameters in the dense layers. And this particular CNN architecture will be best in detecting local patterns and have more efficient parameters, which is what we were going for with the CNN model. So a little bit of details and justifications of why we chose the CNN model here is it has good local pattern detection, which is kind of what we went into in the last slide. It can find short-term trends and patterns such as price trends and momentum shifts. While it was originally designed for images, we can adapt it to sequences, and because stock prices have repeating local patterns, we feel like a CNN can capture them well and predict them. It has robustness to position, and pattern at one time step to another will be detected equally, and it can be considered more efficient than other neural networks as there's fewer parameters. And so here's our LNN model, and LNN models are good for continuous time series modeling, which fits right in with our stock price data set. The model inherently follows the neuron membrane dynamics, which is natural for time series mechanics. It has stable gradients with alpha mixing, prevents of vanishing and exploding gradients, and it's a newish approach, with LNNs naturally being relatively new in research. So here's our model, which shows a hidden size of 48, which is relatively small, but that's due to LNNs being extremely efficient due to continuous dynamics. Shows an alpha of 0.5 for a little testing, and we just thought that would be a good balance between old and new information, controlling the memory versus adaptation trade-off. An activation function of TANH, which prevents state explosion, has its abundant output, a smoother gradient, and mimics neuron activation curves. We decided no dropout for right now, as LNNs have a good self-regularization mechanism, and fewer overall parameters, as LNNs are systematically less prone to overfitting than some other models such as LSTM and GRU. So here's our GRU model, and our justification behind this was the GRU model was chosen as it's considered a simplified LSTM. It combines forget and input gates into a single update gate, and overall it's less parameters with faster training compared to LSTMs. It overall has better generalization to smaller data sets, and it works well when patterns are not extremely intricate but still moderately complex. GRU has faster training times, so more experimentation with the model can be used, and we felt that this might perform well on Google stock, but not so much with the more complex stocks such as the cryptocurrency, and it's less clear with stable patterns. So here's a little bit about GRU model. We chose a hidden size of 128 to provide sufficient memory capacity, and it's not too large to overfit on limited training data. It's a single layer, which is sufficient for most sequential patterns, with no dropout, considering GRU has internal regularization with memory gates. We do have a FC dropout layer, which is light because GRU already regularizes, which is necessary after ReLU. So transformer model, which we chose because it has a self-attention mechanism which can weigh importance of all time steps. It's great at sequencing attributes, which is what it's intended for with NLPs, such as like ChatGPT and stuff like that. Should excel on complex patterns with non-obvious dependencies, and it's best for volatile assets where every and any time step may be critical to predicting the next stock price. It considers global context, which is useful as every time step considers the other time steps. And so for our model, we chose a hidden size of 128, standard size for moderate complexity, with the per head dimensions of 16, which we felt was good enough to capture relationships. We chose 8 heads for complex combinations, which each head learns a different pattern within the data set. We chose 2 layers, one layer to capture the local dependency, and the second layer to capture global dependency. With positional encoding, transformers has no real inherent motion of sequential ordering, in this case a fixed case. Dropout of 0.1, and we chose a relatively small dropout because many transformers have a lot of parameters, and a layer normalization to stabilize training, and which is pretty critical for convergence. An LSTM model, which we consider an LNN model, has its recurrent architecture for memory cells. It has some forget gates, such as a forget input and output gate, which is good for sequential processing that naturally handles time order data. We captured context, so each prediction considers the entire history of the stock, and it also maintains a hidden state which carries information across time. And at the time, or well, still is kind of considered an industry standard prior to transformers. So here's our model. We have varying hidden size per data set, so we chose 256 for Google, has its more stable and it's an overall larger data set than others, and just 192 for the rest, as they're a lot more volatile, and we needed to keep it simple to prevent overfitting. Again, a varying number of layers. We chose a bigger number of layers. 3 for Google, has its complex patterns and stable data, and just 2 for the rest, just to really prevent overfitting. Chose a varying number of dropout layers, with 0.2 for Google for moderate regularization, and again 0.15 for a lighter regularization, and then a different output compression depending on the stock. So for Google, we chose a bigger input to 1, and others smaller input, 192 to 1. We also chose an extra tree model, has their inherently an ensemble method, as to use a number of decision trees to create a prediction. It can efficiently handle a large number of features without any real feature selection inputted by the code, and it handles the high dimensional data with many features. It has a random feature selection at each split, which it reduces overfitting, and randomization prevents overfitting to prevent real market noise to impact the model. It's robust to noise and financial time series data set, which is kind of what we went over right there, and faster training times do not search for optimal splits. So our trees regressor model, which is pretty simple, we just shows n estimators of 100 to get a good number of trees for our model to reduce on. Our learning performance plateaued around 100, so it just kind of made sense to stop there anyway. Our max step was set to none, so we can reach minimum samples. This would reduce overfitting risk, and the ensemble averaging smooths out to individual tree errors anyway. And then again, the random set to 42, which is just really to reproduce in case we need to run the code again, which we ended up doing a lot anyway. And so here's a couple of our predictions made. As we can see here, our extra trees didn't perform very well after their initial point. Our best one was probably the XRP1. You see it's pretty 1 for 1. And then extra trees for Soxel, which was pretty well in predicting data just for around this point. So our XGB model, we chose to use the XGB model, has their sequential ensemble of tree, with each tree corrects the previous error. And gradient boosting optimizes lock function directionally, which has built-in regularization and prevents overfitting. It's relatively interpretable, and we can easily see what features matters most, and it's very efficient with missing data. It's considered an industry standard for tabular financial data. It has proven track record in financial competitions. So here's our model itself. We chose again an estimators of 100 to give good accuracy. And we also had early stopping in case any validation error plateaus, in which the model could stop if it was no longer learning anything really. We set a max depth of 6 here, as it's fundamentally different from the extra tree models. Shallow trees and gradient boosting prevent overfitting, so many shallow trees are better than a few deep trees. And a boosting compounds errors, so we decided to limit the depth to 6. We also set a relatively conservative learning rate of 0.1 to prevent overshooting, and along with the random state, which again is used to ensure consistent results across many runs that we did. So here we go with the XRP performing the best, and Soxel, which we'll call it from now on, performing second best. So here's a little graph, and you pause and look at them, and this was the technical indicators of the time series for XRP. And here's a comparison of learning behaviors. And so we only put a couple up here for now. These were the best performing ones. And for TAN, this is for Soxel and then XRP. So here's a comparison of metrics and inclusion. I'll let you pause this. We're going to go more depth into this later whenever we get through all the numbers here. And so for Google, we found that transformers in DNN had the best performance, as well as an LNN baseline proves that linear relationships exists. And tree models seem to struggle with this stable data. For TAN, we saw most more models perform moderately well. There's clear separation between temporal and non-temporal models. And then CNN's failures with TAN prove that local patterns don't really matter as much as I thought it was previously. For Soxel, we saw that GRU had the best performance despite the small data set. Leverage dynamics fundamentally break down most prediction models, and then extra trees surprisingly perform well in my opinion. For XRP, we saw exceptional results from GRU and extra tree models. The tree-based models dominated due to feature-rich data, and there's high volatility, which doesn't really prevent predictions when overall pattern exists. And then overall, there wasn't necessarily a best architecture in terms of our baseline models. And then we found that data set size matters more than data quality and pattern consistency, and temporal models really outperform on the trade-needy data sets. So here's our tune models. And so for our second DNN round, we went for up to 12 features and added more. The layers got bigger to handle 3 times more input features, and 4 layers seemed to learn complex feature interactions. We also increased the dropout rate for stronger regularization, and we thought the more features creates more risk of overfitting, so the 25% dropout creates stronger regularization for more complex models. Our CNN model, again, we put water filters on it. 64 filters in layer 1 to detect more patterns, such as price spikes and volume surges, and then 96 filters in the middle for peak capacity and complex pattern combinations. We implemented global average pooling so it could handle variable sequence lengths after interpolation, and averages across the entire spatial dimension, single value per filter, as it overall reduces overfitting compared to fixed size pooling. We also increased the dropout rate to 0.25, applied after every convolutional layer, as we wanted more aggressive regularization, as deeper CNNs are prone to memorizing just the training patterns and not generalizing well. Here's our LNN model. We deepened the hidden size of layers for Google to 96 and for others 64. And our alpha level varied again to Google being a little bit higher than the others, as stable stocks benefit more from adapting to faster new data. We also put a deeper output path, or to really additionally nonlinearity refines predictions. We also did a little mixed activation feature here with 10H in the liquid layer to maintain bounding state dynamics, and then ReLU in the FC layers to standard for feed-forward processing. We also lightened up the dropout for lighter regularization to preserve the liquid dynamics of this model. For Greer, we increased the hidden size to 384 to force 3 times more input features, with each feature getting about 32 dimensions. We did 2 layers instead of 1, with the first layer learning basic temporal patterns and the second layer learning higher level patterns, with the interlayer doing 0.15, which is applied between GRU layers to prevent code adaptation. Not within the layers, as GRU cells need full connectivity, and a little bit more moderate rate as it balances regularization and learning. Did a progressive output compression with 3 FC layers for smooth information flow, each of them having the size following standard compression patterns. And we had a little detailed dropout strategy for this one, with the GRU dropout being 0.15, FC dropout 1 and 2, FC dropout 1 being 0.15 again, and then FC dropout 2 being a little bit lighter near the output. For our transformer, we did a hidden size of 384, again 3 times larger with more heads, with more attention heads for more capacity. 12 attention heads compared with 8 in the original model, with each head learning different relationships. We had 4 layers in our transformer, with the first one local dependencies, and then increasing to the global synthesis at the 4th layer. We did a feed-forward dimension with going to 384 to 1536 back to 384 for nonlinear transformation, so it can learn those relationships a little bit better. And we utilized mean pooling, which was using the entire sequence where all time steps contribute equally to new predictions, and it's generally more robust and better for interpolation features. We used a little pre-normalization, which stabilizes training as gradient flows are better in deep neural networks, and enables 4 layers, has post-normalization, struggles with more layers that we have. And we also use Xavier initialization, which prevents gradient explosions, which is pretty critical for these deeper transformers that we have. Here's our LSTM model with, again, various hidden size scaling. Shows a bigger one for Google, has its overall larger data set, and then a smaller one for the others has its more moderate to high volatility and needs a larger model but not as big as Google. We increased the layer depth for Google to 4 layers. Again, it's more large and stable compared to the others, which, while it needs more layers, it's more prone to overfitting. And again, we did a hierarchical learning layers, where the first one is more recent price changes and the last one progressively going down as more long-term context. And we increased the dropout rate as larger models need more regularization. And we also chose a larger output path, which maintains the halving pattern for smooth compression. Here's our last and extra tree model, which we chose a large number of trees for XRP, as it's the largest data set in terms of volume. We wanted to capture more patterns within the massive data set, and just dividing it up between the samples and trees, we just ended up with too many at the original 100 point, and so we just decided to double it. For the others, we decided 100, just keep it the same, and already performed well, so don't mess with it. And here we are. So for Google, we had little issues, but for the other 2 more volatile, it performed very well. And then XGB, we thought it performed very well at the start, so there's really just no changes at all made to this one. And that's because inherently tree-based models are extremely robust in feature count changes, and that's just due to their ensemble nature and built-in regularization techniques, and they're just really great at handling increased complexity without any manual parameter adjustments. So here we are. Again, the first 2 kind of struggle, but Soxel and XGB really performed very well. So here's our metric comparison. I'm not really going to go through these, as we are going to go through them in the 2 slides, but I'll just skip through these and pause them if you want. And so anyway, so the takeaways for the improved models. For Google, we saw that the DNN improved dramatically with additional features, and the transformers really remained kind of consistent. And with the feature engineering, they kind of improved. Honestly, most of them really improved. For TAN, we can see that most models improved, and GRU showed the best gains with potential overfitting issues, we thought. LN improved the most, proving that linear features kind of added a lot of value to them. For Soxel, we saw that marginal improvements overall due to the language complexity, and the extra trees excelled the most, and deep models kind of struggled. And then we thought that architecture kind of matters less than asset fundamentals. For XRP, we saw that tree models maintain near perfect performance, and the deep learning models kind of improved a little bit, and then feature engineering was critical for neural networks on crypto data. Overall, we saw that the feature engineering delivered pretty well, and that there's diminishing returns on volatile assets as they can't really overcome randomness, and then the tree models proved robust to future editions. So here's part 3, addition of meaningful features, and so we did a little bit of feature engineering. Here's a little bit of why. So we saw a couple issues with the raw data. The original features consist of really just 4 basic features: the open, high, low, closed volume, OHLCV, which I kind of went over. We might have mentioned a couple times in this PowerPoint, but we haven't really gotten detailed into it, and because we wanted to wait for this slide really for the feature engineering portion. And that's really because they're missing trends, momentum, and volatility patterns. And there's really no context behind if the price is going to rise or fall over time, and so therefore it has very limited predicting power. And so we thought the solution to this was to add more technical indicators and additional features. And so that's what we did here. So we added these 5 additional features. We added moving averages, which was intended to measure trend direction, as well as exponential moving averages, which is really to place emphasis on recent price changes and attention on faster reaction to changes. Relative strength index, which was for a momentum oscillator, which is really to determine if stocks are overbought or oversold, as well as a moving average convergence or divergence depending on the trend momentum, which was kind of really a buy or sell signal. We also added Bollinger Bands, which is a volatility measure, and a price of rate change. So if we had a positive, there's a bullish momentum, which means that the asset's price is strong. And so here's the formulas. We can pause, or you can pause and read them up if you want to, but we're going to go a little bit more in detail of why we did this and the thought process behind it here in a second. And so I just wanted to asterisk this out, that we did utilize this in improved models. We're not just going to show you another set of numbers again because they were utilized. But we saw moving averages with really 5 levels, 5, 10, 15, 20, which the lower the number means an immediate trend, while the larger the number was just really an overall market sentiment. The exponential moving averages were more responsive than simple moving averages, with recent data weighted a little bit higher. The relative strength index, which was arranged from 0 to 100, which was a normalized momentum indicator, with less than 70 being overbought, but oversold, which means the price may rise. A moving average convergence and divergence, which was a trend following mechanism, with positive being an uptrend and negative being a downtrend, as well as crossover signals with it crossing the line means an action, which shows a Bollinger Band was within 2 standard deviations. The price at the upper band was overbought and you should expect a pullback, which was at the lower band, it's oversold, you should expect a bounce. Squeeze, which is narrow bands, means low volatility, and that likely means a breakout's coming. So part 4 was building our own energy efficiency index. And so what's really the point of this? So we thought that the EEI is an important aspect of this project due to the nature of trading really. And R-squared and MSC are useful, but they kind of ignored the practicality of it. So a computational cost, how much energy does it take for training and inferencing use? A time cost, how long does your prediction take? Can we even use this information within a minute span? how deployable is this? Do we need a data center? Can we run this on our phone? Can we run this on a laptop? This is really important as trading kind of requires speed. We must be able to really build a model to predict as fast as possible, as that can mean a lot of money coming your way. And scalability also matters. If we predict 1,000 stocks 1,000 times a day, that's a million prediction to potentially earn money. So our formula, I'll pause here for a minute just to give you time to read this. So we thought it was justified as our dimensionality is kind of consistent with an accuracy score between 0 and 1, so it's dimensionless. And energy cost always outputs a positive real number. We chose monotonic properties such as higher accuracy is high EEI, while higher energy is lower EEI, because we want a high accuracy but a lower energy cost. And also capture trade-offs, and our real-world validation has our EEI capture 3 factors that closely align with industry practices. And here's our visual. So we see that the D and N's dominate efficiency, the trade-off being between energy and accuracy, and our improved models show mixed EEI results. Alright, that's all. I appreciate you for coming and listening, and thank you so much for this class. Big data is very knowledgeable and very good for us.